back. Now I feel like we can really start putting this all together. So I think this is maybe, I don't know what I'm on, 15, 16? 16. 16, all right, fine. 16. Impedance. Impedance. All right, so in an AC circuit, or an AC circuit, yeah, an AC circuit, we'll do that. Circuit can be described by its components. By its components. So if it's purely resistive, which means only resistors, then we would call it an R circuit. It has an R. So purely capacitive, which is only capacitors, then it would have a C. And if it's purely inductive, which is only inductors, then it's an L circuit. All right, so then we can combine them up. We could have any combination. We could have an RC circuit, which would be resistors and capacitors. We could have an RL, which would be resistors and inductors, or we can have an RCL, which would be resistors, inductors, and capacitors. Okay. Okay, and then take it back a little bit. We talked about the fact that, well, resistors have resistance. But then we said with both capacitors and inductors that we expressed in ohms, but it's not considered resistance because of the phase shift. Not right, Oscar? Yeah. Okay. So, if it's not resistance, we can't just add it like a resistor. We can't say that we have 100 ohms of resistance and 100 ohms of X of L and 100 ohms of X of C and go, well, that's 100, 100, 100. Well, that's 300. It would be nice if we could. We'd be done for the week. But it doesn't work that way. So, any circuit that is not purely resistive, must have total opposition to current flow represented as impedance. Which is represented by the letter Z, or Z, I think, if you're from England. You stretching or a question? You're not going to ask me why, are you?
No. We kind of went past capacitors.
What's that?
I have a capacitor question.
Capacitor, yes.
Capacitor discharge.
Capacitor discharge. 5 time constants.
So we have a component that has capacitive discharge.
You're talking about capacitive discharge components?
Yeah.
Yeah. You're talking about like high tension ignition systems on turbine engines, capacitance discharge. Or in the same thing, strobes.
If you have a minute, like anytime, could you go over that?
That is something Phil does in his class. Oh, you already had that.
Fucking mind blown and didn't know what was going on.
All right, if we get time. All right, impedance is not the sum, as I just said, not the sum of each, but a vector sum. Oh yeah. See, they don't laugh. They're like, I don't get it.
Oh, come on, it was good.
They're just scared right now or something. I don't know.
I gave one solid nose exhale.
One nose exhale, or just one side.
Yeah, only one side works.
Okay. All right.
Yeah. We need to see that video again.
Huh?
More for the emotion.
Oh yeah! Somebody give me the tracksuit. All right. A, B, C, D. All right. Because capacitors, which is X of C, and inductors, X of L, have opposite effects. And what are those opposite effects? One current leads and the other one voltage leads. X of C is ice, current leads the voltage. X of L is Eli, so voltage leads. So if they were in balance, they would cancel each other out and we would have no problems whatsoever. So you would have, if you had 5x of C and 5x of L, you'd have 0, and then you would default to it being a purely resistive circuit because they have opposite effects. So because, did I finish writing that? Because they have opposite effects? Oh yeah. You're not going to love this. We can use algebra to find, told you I wouldn't like it, total reactance for, I put for a CL circuit, but really RCL will be the same thing because ours circuit, or any circuit containing both capacitors and inductors.
How do we cut it?
Yeah.
With the different circuits, the RCL, is that like the specific order they should be in? Like, is CL more correct than the...
I put RCL. It's just the way it rolls off the tongue here. I don't know if there's any convention. All right. So X of L, what's X of L? Nope. X of L, inductive reactance. Everybody's got to stick with me on this.
That's the effect.
Inductive reactance, that is the ohm version for inductors, will be positive. X of L will be positive because it causes voltage to lead, because voltage leads. And X of C will be negative because voltage lags. X of C is capacitive reactance. It is the equivalent to capacitive resistance. Does that work? X of L, inductive reactance, is like saying inductive resistance. They could have called it that. I think that would have been much nicer, wouldn't it have been? Everybody follow?
Somebody needed their name or something.
Yeah. All right. All right. Let me see. So the formula that I would write down on this paper is X total. X total equals X of L, which is positive. This is terrible. This is the way the book does it. Minus, plus a negative X of C, which we could also do X of L, X total. X total equals X of L minus X of C. And that would work out fine because you'll still get a positive or negative number. So I prefer the x of L minus x of C. It works. All right, but like I said, because impedance here, go back here, impedance, Z is a vector sum, this is what we're going to do. We're going to graph it out. Make it large like this. So everything above the line will be x of L, and everything below the line is x of C. Not that it matters. We could just do it either which way. This line right here will represent resistance going out. And we have to figure out then the hypotenuse, which is the angle of a triangle. So, for example, if we had, if x of L was 10 and x of C is 5, then x total equals what? 5, right? So that's a positive 5. So it's a positive 5. So we go up 1, 2, 3, 4, 5 and say it's right there. And then if I said my resistance was 20, then we'd count out 1, 2, 3, 4, 5, 6, 20, and there's my resistance right there. Then impedance then becomes whatever line this is. We have to figure out the length of that line, and whatever the length of that line is, that is Z, our impedance. That's how we figured out a vector sum. So if we had x of L is 10 and x of C is 10, then x total is
10 squared plus 5 squared equals 125.
wow. Let's back up the truck here, buddy.
Negative 5.
10 minus 10 is,
0.
So
you don't got to make it hard. X total, if x of L is 10 and x of C is 10,
oh, okay, so 5.
no, I did. I said both 10.
V0.
The first time I did 5. So if x of L is 10, do I have to write it down? X of L equals 10 and x of C equals 10, then x total equals 0. All right, so then 0 would be plotted on the line right about there. And if my resistance was 20, what would impedance be? I'll tell you right now. 20. All right, you guys are with me. All right, what if x of L is 10 and x of C is 15? Negative 5. 1, 2, 3, 4, 5. Now, it doesn't matter. You could have just went up 5. But here's where it matters the most. If it is a positive number, a positive, meaning more x of L, then the circuit is inductive. If we have a negative, meaning more x of C, then it is a capacitive circuit. That is on the test. Most people miss it. You're going to do all of this work. You're going to come up with an X total, and you go, I don't know how to do it. You shouldn't. So I'm stressing it right now because maybe I don't write in my notes somewhere very well. All right, we ready for this? How did I just manage to swap pens in my hand? Oh, there it is. All right. So looking back at our drawing of the graph, the length of the hypotenuse line, that was the line we had to draw. That's this line right here, Z. That's called a hypotenuse in a triangle. The length of the hypotenuse line indicates Z. Indicates Z. All right, so in a series circuit, and you'll be happy to know we're just going to do series. In a series circuit, Z can be solved by the Pythagorean theorem. I'm going to try and spell it right. Pythagorean. Pythagorean theory, which is a square plus b square equals c square.
That's what I was saying earlier.
I know, but you were like 8 steps ahead of us. That's going to confuse you because I was talking about 10 minus 10 and you're over here with your squaring and whatnot. It's like, come on, man. Slow down with the rest of us. I have a couple of different versions here. I'm going to talk about each one. So before you add them to your x total square equals, x total square plus r square equals z square. I have z equals the square root of r squared plus x t square, and I have z equals r squared plus xl minus x c squared, and that's the square root of. I probably should have made these all on separate lines. And what I want to tell you is all of these things are the same. I prefer to use this one. I don't care which one you use. But I will tell you why I like that one. Because it is, to me, the most simplistic way to deal with it, because I like to do step by step by step. If you use the last one, you can actually combine your x of L and x of C and solve for that. But that becomes a problem if I asked you, what is x total? You'll be like, crap, now I got to do x total. Then you've got to plug this back in here. But if you already have x total, then why not just use the middle one? So I'm going to use the middle one, but you can use any one you like. So if it were me and I were writing stuff down on my formula sheet, I would write z equals the square root of r squared plus xt squared. And if we look at what we're talking about z. We've just rearranged this equation up here, where it's basically, turn it around backwards, c squared equals a squared plus b squared, right? I just turned it around because we're solving for c, and then get rid of the square the square over here, which is c equals the square root of a squared plus b squared, and that is exactly what that is right there, and that's why I like it. I told you it would be simple.
No, but that formula of reading it.
All right. So this is a repeat, but just so Z, which is impedance. Impedance gives the total resistance, of an RCL circuit. All right, that's what we've been saying. Now, I want to tell you that right now you may be thinking, there's no way I'm passing this. But let me tell you, when we put it all together, you're like, okay, wait a minute, that was actually really easy. As long as you're paying attention and kind of going, I get this, I'm sort of following you, sort of, for the most part, I'm writing my notes. It's not going to be that bad. It really isn't, because I'm going to show you how. Okay. But it's going to get a little worse right now. And then we're almost done. We have to talk about phase angles. Because when things get out of whack like they are here, that's not a good circuit. It's out of balance, right? We have too much x of L. And if we were going to design this, we'd have to bring on
Capacitive.
capacitors to bring the X total, or X of L, back to 0. So when we're analyzing this circuit, this little angle right here is our phase angle. So the higher up it goes, the worse the phase angle is. When it comes down to nothing, we have a 0 phase angle, right? So if it was all the way up here, it'd be at 90 degrees. That'd be really bad. I don't even know how that would look on the graph. So I guess it goes way up. Okay, so we have to figure that out. So here we go with that. So that was like, I don't know, F, this is G. I don't know, I'm just skipping around, so I'm very sorry about that. Leaving out the stuff we don't need. So the position, you can make it a star or a circle. The position or angle, the angle of the line of the hypotenuse, indicates phase angle. And phase angle is the difference between, phase angle is the angular difference, between voltage and current. This pen is squeaky. Phase angle is represented by the Greek letter theta. By the Greek letter theta, which is kind of like this. Theta. So we know a couple of things. In a purely resistive circuit, purely R, phase angle will be what?
0.
All right. 0 degrees theta. We know in a purely capacitive circuit, the phase angle would be
270 or minus 90.
minus 90. And why do we know that? You're thinking, oh shit, I didn't know that. We've talked about it. And if we think about the graph that we drew, the purely capacitive, just all capacitors, we talked about earlier that we can go way back to another drawing, which I don't even know if I could find, when we're looking at a sine wave. And we said that in a purely capacitive circuit, we have Eli, the Iceman, ICE. So what leads, what lags?
Current leads voltage.
All right, so in a purely capacitive, as soon as we come off of 0 volts, what happens?
The current goes to max.
Current goes to max. So that means that it's actually going like this, right about there. And so the difference between the peak here and the peak here is how many degrees?
90.
90 degrees. Okay, that's where we come up with. It's out of phase, negative 90, looking at our graph. And then in a purely inductive circuit, it's going to be
90 degrees.
positive 90 degrees. Or you can just say 90 degrees. It's 90 degrees out of phase. Because the opposite is true. So if we drew something with an inductor is going to be, let me see, maximum will be here, so it'll be going more like this, so we're at 90 degrees off that way. All right. Yeah. So we're off that way. All right. So to compute the phase shift in this circuit, we're just going to look at triangle now. We need a triangle. We're going to use the trigonomic functions. And in a triangle, a right triangle is called a right triangle because this is 90 degrees right there all the time.
Yep.
All right, so if we use sine, cosine, and tangent, and we know the angles, we could find the length. That's what that does. But we're not going to do that. We aren't going to know the length, so the length is going to be a question. Well, we're eventually going to figure out the length. I'm sorry. We are going to know the length, but we're not going to know the angles. We'll know this one is 90, and we know the other two are going to add up to 90, but we need to find out this angle right there. We need to find it. So if we know the length of all the sides, then we use the arc functions, arc sine, arc tangent, arc cosine. So you follow what I'm saying? If you know the angles, you can find the length. But that's not what we need. We don't know the angles, we know the length. If we know the length, then we use the arc sine, arc tan, arc, whichever one I just didn't say, cosine, to find that angle. And we find that angle right there, then we're going to have our angle. And so it's not really very difficult. So again, we're going to use that. So let's see. Oh, so we need to know a couple things. So this leg right here is always called the hypotenuse. Always called that. And if we are referencing this angle right here, which we are, that's the angle we want, and we're looking at this angle, we're going to realize that this side over here is the opposite side, because it's the opposite of that. And this side right here is going to be the adjacent. Adjacent means next to, because it's next to. So ADJACENT. So this is the adjacent side right there. So all right, we have three sides now. The opposite, because it's the opposite here we're looking for. We have the hypotenuse, because it's always called the hypotenuse. And we have the adjacent, because it's next to it. Everybody good? Making it simple, right? All right. Then we have the functions, sine, cosine, and tangent. You get to choose which one you want, and I don't care, but this is how it works. If you want to use sine, let me see. I can never, it's SOHCAHTOA, but I always have to look how to spell it, because I know so it's called SOHCAHTOA, 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 which means that sine is the opposite, and I'll explain this really well, over hypotenuse. Cosine, see, opposite hypotenuse. Cosine would be adjacent over hypotenuse. And tangent is opposite over adjacent. Which is to say that if you know the opposite and the hypotenuse, you would use sine. If you know the adjacent versus, if you do the adjacent and the hypotenuse, then use cosine. If you use the opposite and adjacent, you can use tangent. We're going to know all three sides, so you can use sine, cosine, or tangent. You'll get the same answer. And I'm going to show you how to do that. So let's see. I am running out of space here. So let's say, all right, I'm going to have to, can I delete this? Okay, I'm deleting in 3, 2, 1, delete. Yes. But we're going to use arc. Arc just means the opposite. That's a function on your calculator. All right, so you're going to have circuits that'll, if I just drew a circuit, it'll look like this. And you don't have to. So RCL, right? It's got inductor, capacitor, resistance. So I could say this has 10 ohms. I could say, I made it easy here. Eventually I'm going to give you the henries and the capacitance, but I didn't on this point. So ignore that. I thought I did. So my example is we have an R equals 10 ohms. I have X of L, because I made it really easy, has 30 ohms. And X of C equals 10 ohms. All right? And then we look at our triangle. All right. So my adjacent side, that bottom right there, how long is that? That is 10. Very good. This side right here, that is 20 because it's 30 minus 10. X of L going up, X of C going down. 30 minus 10 is 20. So now I need to know what is Z, my impedance, the hypotenuse. So how are we going to figure that out? Yeah, okay. So honestly, we actually have enough information here to complete this angle. If you have two things, you can know the third. And I can show you right now. So we had SOHCAHTOA. So S equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And TOA is opposite over adjacent. What do we know for this angle? Which two things do we have?
Opposite.
We have the opposite and adjacent. So which one do we use here? All right, we'd have to use that, the tangent. All right, so the way we do this, I'm going to have to do it with my calculator first because I switched calculators. All right, so SOHCAHTOA, so we have tangent equals the opposite, 20 over 10. So that's 20 divided by 10. Okay, so on your calculator, you're going to do this. You're going to go second function, a little blue one up here. Then you're going to hit tan. See, the sine, cosine, and tangent are all in a line. So second function tan, and you should see on your calculator tan minus 1. That's arctangent. That's the opposite of tangent. That is used for finding the angle when the sides are known. And so your calculator should look just like that. Everybody with me so far? All right. Then we're just going to put 20 divided by 10. And then I close the parentheses. So 20 divided by 10, probably don't even have to close the parentheses, equals 63.4349. You're done. That's the angle of theta. That wasn't hard, was it? Yeah.
You got 20 from the x of L minus the x of C?
That is correct.
You said that function was called arc what?
Arctangent. So it's sine, cosine, tangent, but because we're using the tan minus 1, cosine minus 1, and sine minus 1, it's called arctangent, cosine. Or we could just say tan minus 1 or s minus 1. All right, let me see. That's it. There's your phase angle. I mean, boom, you're done. Okay, now let's figure out what is z. What is z right there? So z, and so on your formula sheet, I would have this on there. I would just put that right there. S equals O over H, C equals A over H, and T equals O over A. Oh, I do have a note on my little notes here that says, make sure that your calculator is set to degrees. You don't have to, so you hit the button right next to, if you're getting the wrong answer, it's right next to the second function. You have degrees, rad, and gradient, GRD. Make sure it's on degrees. All right, moving down. We're going to solve for z. So z equals the square root of r squared plus xt squared, right? Yes, I was right. Okay. So z is equal to, my r squared was 10 squared plus, what is it, 20? 20 squared. Now I think using this calculator, you can do the entire function inside of it. Nope, it said error. I probably did it wrong. What's that? Yeah, I must have fat fingered it. I don't like to, and I'm okay if you do. I actually like to do it like this. 10 squared plus 20 squared. So I'll just do 10. This has x squared plus 20. X squared equals, and I get 500, the square root of 500. And then I'm just going to do square root. Oops. Second, square root, 500 equals 22.36. So z equals 22.36. What is z again? It's the hypotenuse, and it means it is the impedance. A vector sum, a vector which has both direction and magnitude. Oh yeah. All right, so that is 22.36 ohms of impedance. And now we've hit the peak. Oh, we're gonna go back down. Yeah.
In finding the phase angle, is it always going to be that essentially right corner?
It is always going to be that corner.
Okay.
Always. Because if you do left corner, it's 90 degrees.
Right, but the one above that.
But then you would have to subtract that from 90 to get that.
Okay.
Unless it's 45. Then it is that same. If you didn't follow that, don't worry about it. All right. If you made it through that, you've made it through the tough part. Now we just got a few little things to tighten up here, and then we're going to go back through and do example, 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 example. And we're going to put it all together and just do it all over again. So now we're going to talk about power factors. And this is, you going to be all right?
No.
You will be. I nearly promise.
Promise. 60% of the time it works every time.
How many bags of
So I was trying to think, how many bags of corn nuts? Well, but I know you'd probably just fail it on purpose to get a bag of corn nuts. Be like, all right, I got it next time, it's cool. Be over there figuring out how to get a 69 in a bag of corn nuts. All right. There are two types of power, although I think there's three I'm going to use. There are two types of power used to describe work. Used to describe work. Work in an AC circuit. In an AC circuit. True power in watts. In watts. Actual amount of power consumed by resistance. So power consumed by resistance, not counting impedance, Z, inductance or capacitance. So it's measured in watts, which I already said. Symbol is right, P. Very good. Okay, P is a function of circuit's dissipative elements, resistance. Power total equals I squared R. And we're going to use that formula this time. So I'd write that down. Power total equals I squared R. And then we have apparent power. Apparent power is the power consumed by the entire AC circuit, resistance and reactance. So it's R and Z this time, all put together. So it is taking into consideration Z, which is taking into consideration the effect that the coil and the capacitors have on the circuit. It is a product of volts and amps. product means multiply. So I just said it is V RMS times amps RMS. If you're doing it that way, I think you can do it. The way we're going to do it equals apparent power. Apparent power. Or I have it as P apparent. P apparent, which is not taking into consideration the RMS value, equals I squared times Z. Expressed in volt amps. I shouldn't put the dash there. It makes it look like I'm dividing. Volt amps. Volt amps. And it will always be more than true power in a circuit with X of L or X of C. Why? Because now we're adding in the X of L, X of C, and the resistance, so it's got to be more. So true power based on resistance, our volt amps, our apparent power, taking into consideration and adding X of L, X of C. VA. I know. How are you going to remember that one?
What does the RMS mean next to the
Root mean squared.
Root mean squared.
So I would write down the I squared times Z. So power apparent E equals I squared Z. And if you aren't getting these, that's okay. We're going to go back through it in an order, and you may want to get your sheet and reorder it and say do this, then this, then this, then this, and then you're done. Last thing is the power factor. Power factor. It is the ratio of true power to apparent power. So it is PF, power factor, equals true power over apparent power. Your answer will be a number between 0 and 1. So 1 is purely resistive, purely R, and 0 is purely reactive, meaning all X of L or all X of C. No resistance. The lower the number, the larger the phase shift. Because the lower number, again, is purely reactive. So that means along the opposite side of the triangle, it's going to go very high. And the resistance is going to be very, very short. The lower the number, the larger the phase shift. Yeah.
The R next to one is purely R. That's resistive.
Yeah. Purely reactive. Oh, R is resistive. R.
Resistive.
Yeah, RCL circuit. R is resistive. The larger the phase shift, and the lower the efficiency. All right, we good? All right, quiz tomorrow? You know me better than that. All right, so what this is going to look like. Did everybody write that down? Okay. Is tomorrow we're going to work on stuff like this. Well, not stuff like it. We're going to work on exactly something that looks like this. I got to find my notes so I can even know what it is I'm going to write here. There we go. I'm going to give you a circuit that looks like one I drew before. That's it. And then I'm going to say something like, we'll work on this one tomorrow actually. So this is 440 volts at 60 hertz. And we've got a resistance of 500 ohms. Oops, that over here, 500 ohms. And that means this goes away. And we have an inductance of 3.5 henries. And we have a capacitance of 12 microfarads, FD, farads. And we're going to solve that and do all the work that we just did and come up with an answer down at the end.
This is similar to the worksheet on the lecture in front of the campus.
This
Yes.
is exactly, I just copied out the first problem. So it's just a worksheet. Because people ask me, oh, I want a worksheet. I'm like, okay, here's a worksheet. Which is not mandatory.